Now in this lecture video, we're going to look at how to compare the means of two populations using dependent samples. So suppose that the samples obtained from the two populations are not independent, but dependent in some way. For example, observations from the two samples may be matched or paired. For example, suppose we have paired samples from the two populations, the two sample sizes both being equal to or being denoted by n. So y11 is the first observation in the first sample, y12 is the second observation in the first sample, and so forth out to y sub 1n, the last or nth observation in the first sample. This is our sample of size n from population 1. We'll denote the mean of that population by mu sub 1. And then y21 is the first observation from sample or in sample 2. Y22 is the second observation in sample 2, and so forth, out to y sub 2n, the last or nth observation in sample 2. And we'll denote the mean of this population by mu sub 2. Okay, now the other part of this, the other part of the structure of this sample, of these two samples, is that they're not independent. Y11 and Y21 are paired. They are both the first observation in their respective samples, and they're both measured on the first experimental unit. Likewise, Y12 and Y22 are both measured on the second experimental unit, and so forth out to the last pair, Y sub 1n and Y sub 2n. These are both measured on the nth or last experimental unit in the sample. And so that's what we mean here. Y sub 1j and Y sub 2j are paired for each j going from 1 to n. And so in this case, the procedure based on independent samples should not be used because the samples are not independent. They can't be, right? We would expect that the two observations on a given subject or experimental unit may very well have a non-zero correlation. Well, if the correlation between the two observations is non-zero, then they cannot be independent. All right, and so the procedures for independent samples should not be used. If we were to use the procedures for independent samples, then we would most likely be throwing out a lot of power. And so the way that we're going to analyze this kind of a situation, analyze these kind of data sets and compare population means, is to reduce it back to a one sample problem. And we're going to do that by taking the difference between the observations within a pair. And so, for example, notationally, we will denote the difference by d sub j. All right, and so this is the difference between the first and second observations for the jth experimental unit, j going from 1 to n. And so then, instead of having two dependent samples, we have one sample of differences, d1, d2, and so forth, up to d sub n. And so this represents, because the individual samples, even though they're paired, they were considered to be jointly a random sample of the paired observations. These differences then represent a random sample from the population of differences of paired observations from populations 1 and 2. All right, so with that in mind then, let's think about what the mean of d sub j is. Well, because expectation is a linear operator, the expected value of d sub j is equal to the expected value of y1 sub j minus the expected value of y2 sub j. Well, each of these, y1 sub j has a mean of mu1, and y2 sub j has a mean of mu2. And so the expected value of d sub j is mu1 minus mu2, and so that's what we're saying here. So we get this result by virtue of what we know about properties of expectation that we learned back in the section on probability and distribution theory. Okay. Okay, so the mean of the distribution of differences, which we could denote by mu sub d, expressed in terms of mu1 and mu2 is the difference that we're used to. And we will denote the variance of the population of differences by sigma squared sub d. All right, and so then testing and confidence interval procedures involving mu sub d, which is equivalent to or equal to mu1 minus mu2, can then be restated in terms of mu sub d itself, and based on the sample of differences using the procedures for single populations that we discussed back in Chapter 4. And so then this becomes just a one sample problem, a one population problem. It becomes a problem involving one population mean, mu sub d, all right? But we would be keeping in mind that that is equal to the difference in the population means. And so here are the hypotheses that we can test, expressed both in terms of the difference mu1 minus mu2 as well as in terms of mu sub d. And so we can express these hypotheses either as in terms of a single population mean or as the difference between two population means. As before, d sub 0 represents the hypothesized difference, and in some situations, in many applications, but not all, that hypothesized difference would be 0. But again, like I said in a previous lecture about this, it's not always going to be 0, and so you need to think about the problem and think about what makes sense in the context of that problem. What question is trying to be answered? And the question that's trying to be answered will drive the hypotheses. They will determine the hypotheses and the appropriate value for the hypothesized difference. So you always, always, always have to take that in mind and be consistent with what the problem is asking you to solve. Okay, so if the hypothesized difference is equal to 0, then we can state the hypotheses in these three ways. So for the three types of hypotheses: a two-tailed test, a left-tailed test, and a right-tailed test. And for each of these, we can state the hypotheses either in terms of a difference between the two population means or in terms of a single population mean. And so again, we see that how to express these hypotheses in those two ways. Okay, so by focusing the analysis on the paired differences, the problem has been transformed from a two-sample problem to a one-sample problem, which we studied back in Module 4. Therefore, the test statistics, the rejection criteria, the p-value formulas, and so forth from Module 4 would be used to analyze the sample of paired differences. And in particular, we would be using, more than likely, because we more than likely don't know what the variance of the population of differences is, we would have to estimate it, all right? And so we would be using the one-sample t-test, to do this. And so it really simplifies to something very simple to do. Because procedures for testing hypotheses about a population mean, in particular, like I just said, the one-sample t-test has already been looked at. And in addition to that, we've looked at constructing confidence intervals for a single population mean, and so that would allow us to use that same type of procedure for testing hypotheses about the difference mu sub d, or the mean of the differences. And so we could use all those procedures back in the section, or the section on the one sample t-test to make inferences, to analyze a paired data set or paired samples, and to make inferences that allow us to compare the two population means. So we're not going to get into any more examples of that because we've already seen some examples. So that is the end of this particular section hypothesis test for population means. We've looked at several situations. We've looked at comparing population means when we know the population variances. We've looked at and again using independent samples, right? We've looked at how to compare population means using independent samples when we don't know the population variances, but when it's reasonable to assume that those population variances are equal. We've looked at how to compare population means using independent samples when we don't know the population variances and when it's not reasonable to assume that the population variances are equal. And then finally here we've looked at how to compare the means of two populations using dependent samples. So you really have to pay attention to what's going on in your data and the nature of the samples. Are they independent or not? And you have to think about the population that you're dealing with. Do you know the population variances of those populations? In a few situations, you may have pretty good information about what those variances are, but in most cases, you're not going to have enough information to really know with a lot of certainty what those population variances are. And so you're going to have to estimate those population variances from your data. And you will again also have to make a determination, is it reasonable to assume that that the population variances are equal? And you'll have to make that determination using your data. So you'll have to make an inference about the population variances. You'll have to compare those population variances. And so that will involve hypothesis testing and possibly constructing some kind of confidence interval for the ratio of the two population variances. So that is the end of this section, and we will get into the last section in this module in the next lecture video.